So to start off our last Unit 7, we're going to take a look at the second fundamental theorem of calculus. Now, the first fundamental theorem of calculus that we were looking at in Unit 6 was if we were to work backwards from some function, in this case I'll just say it's f prime, then we are able to, or at least on some interval from a to b, then we have to first of all find the antiderivative. So if we work backwards from f prime, that would be f, and then we can do top bound of b minus the top bound of a. So this is the first fundamental theorem of calculus that we dealt with a lot in Unit 6. Now we're going to take a look at the second fundamental theorem of calculus quite a bit in this Unit 7. And the second fundamental theorem of calculus kind of tells us a method or a technique to help us take the derivative of an integral. Okay, so what's going to happen in that case if we take a derivative of an integral? So we're just going to explore two examples and see if we can try to find a connection between the two. So we're going to say use capital F equals the integral from 1 to x. Notice how this is a little bit different because now we have a variable as one of the bounds, not strictly numbers as we've seen previously. So the antiderivative of little f is capital F. So we have this connection with integrals and antiderivatives. So in our first case, we're going to say little f of t is this function. So I'm just going to kind of replace that in this spot. So capital F of x is the integral from 1 to x of 4t minus t squared, and don't forget that dt on the end. So I'm going to use this first fundamental theorem of calculus to help me work backwards, and then I'm going to plug in my top bound of x minus my bottom bound of 1. So if I work backwards, this would be 2t squared minus 1/3 t cubed. And if I plug in my top bound of x, I'll get 2x squared minus 1/3 x cubed. And then I have to subtract what I get when I plug in my bottom bound of 1. So this would be 2 minus 1/3. So in the end, capital F of x is 2x squared minus 1/3 x cubed. 2 minus 1/3 would be 5/3, so minus 5/3. So this is what I get for capital F of x. Now they also want me to find the derivative of this capital F of x. So now that I have the function, what's going to happen if I take the derivative of it? I'm going to have 4x minus x squared. All right, let's go ahead and try another one. So capital F of x is the integral from 1 to x of cosine t dt. So if I work backwards from cosine, antiderivative would be sine. And then I'm going to plug in my top bound of x and subtract, plugging in my bottom bound of 1. So there's my capital F of x. If I were to take the derivative of this function, the derivative of sine is cosine, and then subtracting the derivative of a number, I don't really know what sine of 1 is, but if I were to take the derivative of a number, that would just be 0 anyway. So here's my derivative and my f of x function. Now, what I want to try us to do is take a look at something here. Notice how we originally started with 4t minus t squared as the function within our integral. And if you take a look at what happened after we worked backwards and then took the derivative, I have 4x minus x squared. This function looks very similar to the one that we started with, just instead of having t's in it, we have x's. Maybe there's a connection there. So, same thing kind of happens here. Notice how my original function I started with was cosine of t, then I worked backwards and then took a derivative and I got cosine of x. So they seem to follow a pattern of being the same exact function if you were to take the derivative of an integral, but in this case, instead of having a t in there, we have an x. Let's see if the same thing kind of holds true for the bottom two examples. So I'm going to have a very similar setup. This time, however, notice how my integral is from 1 to x squared. Okay, not just x like it was in the last examples. All right, so if I work backwards, I'll have 1/4 t to the 4th. Plugging in my top bound, I'll have x to the 8th. And if I plug in my bottom bound, I'll have 1/4. All right, so that's what I get if I work backwards. And then if I take an integral, I'll have 2x to the 7th. So something interesting happens here. Notice how this ending derivative result does not exactly match what the function was that we started with in this integral. But maybe we can start to see a connection here, and we'll get there in a moment. Let's try the next one. So if I work backwards, let's rewrite the power of a half instead of a square root. So add 1 to the power would be t to the 3/2. Divide 6 by this new power of 3/2. That would be 12/3, which would be 4. All right, plugging in the top bound, I'll have 4t to the 3rd. And if I plug in the bottom bound, I'll get 4. And if I take the derivative of this, I'll have 12t squared. Okay. Again, notice how this derivative result we got did not exactly match the function that we had. So we're going to try to find a connection here to help us answer the question, what's going to happen if we take the derivative of an integral? So if I were to put a prime mark on this side, what would happen to this side? What happens if you take the derivative of an integral? And it seems like in our first two cases, the derivative matched the original function we had, just with an x instead of a t. In the last two cases, that really wasn't the pattern that we had here. These should have been x's. That's my fault. So there has to be something new here, and perhaps the reason for that is because we changed the bounds. Instead of just a single x, it's now an x squared. So let's see what kind of happens here. Notice how the original function was t cubed, so perhaps I could write this as x cubed, but that means I'd have to be multiplying by a 2x to the 4th. Okay, this is what I was anticipating to get as my derivative result, but notice how there's some extra piece here. We could do something similar over here for this one to see what our extra piece was, but the moral of the story is that we have to be careful as to what the bound is. It seems to be if the bound is just x, then it's going to match. If it's not just x, it's going to be something different. So we have to be kind of familiar as to what to look for and be careful about what it is and what it's not. But there is some generalization that we're going to use, and that generalization is called the second fundamental theorem of calculus.